Okay, let's start. So we are approaching the end of this first third, or I guess more of a half of the course, where the focus is on algorithmic ideas and computations. So I'm going to soon leave the stage to Sasha to get you a bit more of the under the hood of the statistical aspects. This last week, the dominating theme is going to be essentially data representation, which is kind of the elephant in the room. Representation, it seems okay. So, what we've done so far is that in a bunch of different ways, we said giving labeled data, try to find a function f of x, and we consider mostly linear models, but that's because we show in a bunch of different ways that nonlinear models can be similarly dealt with, and we saw how if you look at features or kernels, you can pretty much generalize the results to these different models. And what we spent time thinking about was, okay, how do you estimate W? And the idea was you use the data as a reference. I think I mentioned this summary a bunch of different times, so I'll make it short this time. But let's just say we focus on estimating W. I think we all agree on this, okay? And then we just give you a couple of different ways of what is the entry point to change phi, okay? But we've only discussed features and kernels, okay? What we want to do today is to think again about this. And basically, the idea is in this class and the next, I don't know if Andy updated the syllabus. There is a little bit of an update. So essentially, today is going to be about unsupervised learning of data representation. So we're going to go from dictionary learning to autoencoders. And we're going to discuss everything unsupervised. And then Thursday, we're going to discuss essentially how we're going to introduce neural networks and deep learning, but we're going to somewhat introduce it in such a way that well, the main motivation would be to view it as a way to do supervised learning of data representation. Okay, so in some sense today is going to be the preparation to that. So the idea today is essentially to discuss more about where this phi comes from. Okay. So so I guess let's start with the names. Okay. This is a classical object in a bunch of different fields, so we call it features, feature map. We saw that this is related to kernels. If you look at signal processing, you often find, it's pretty general, right? It's given a data space and a space of representation, a feature space, okay? And typical example is RDRP, but we can take more general scenarios. The idea is that you just do transform your data, and the idea is that you transform your data in such a way that they are easier to be handled, or that they allow somewhat subsequent tasks to be easier to perform, okay? We're gonna expand a bit on this. So you find very much related idea in signal processing where this phi is either called a transform. Think of Fourier transform, wavelet transform, Radon transform, all the kind of transformation that take an input space and send it somewhere else, or an analysis operator, as in, say, Fourier analysis, okay? The idea that you somewhat want to now represent your data by some list of numbers that are somewhat meaningful in some precise sense. In information theory, the idea of, a very related idea is the idea of encoding, okay? You have a data and you want to map it in a suitable encoding that is somewhat capturing what's contained in the data. Say entropy information is the kind of main goal, main quantity that are interested in the contest. And then you have yet again, things like in computational geometry, you have the notion of embedding. Okay? Somewhat again, you map your data into a new space, and this is an embedding of your data in this representation space that should somewhat preserve some kind of information. I mentioned this list because, as you'll see, there are different ways to look at all these different quantities. And basically, what we discussed so far is only these two examples, but you have many, many other examples where you essentially go and steal from these other fields. And that's kind of the way you do when you think of looking at data representation by design, okay? Rather than trying to learn phi. Phi is not part of any learning process, but it's actually a part where you go to an expert and you learn what are the mathematical tools to try to describe phi, and then you go to an expert and you try to ask him what are the really important information about this problem that I should try to design into my model, okay? And that's the entry point. And so, we've seen kernels and features, but if for any modalities, for example, you take vision, there has been years and years of way to filter data appropriately, okay? So wavelets in an example, there are things like SIFT, hogs, various kind of parameter, pyramid kernels, and so on and so forth. And you can go on to other modalities, to take signals like audio and look at things like MFCC, I cannot pronounce it. And you can keep on doing. You can try to see, for example, different kind of encoding coming from information theory, different term of embedding from computational geometry. We've discussed, for example, Johnson-Lindrester's ideas. So these are all examples of ideas that are relevant for us. They're just like a book of tricks, if you want. But what they have in common is that there is no learning in none of them. Okay, each one of them maybe use some stochasticity, as in the case of Johnson-Lindrester's, but each one of them is somewhat trying to describe a phi by some kind of design principle. So the question we want to ask today is, can we learn it? Can we learn it somehow? I've framed some of the, the aesthetic, it's of course an important question from a conceptual point of view, but even in practice, it's really somewhat, I said it's an elephant in the room because it's really the important question. It's quite well known that in most applications, depending on the kind of trick we use to learn the W, you get different results. But what usually makes a huge difference is phi. Okay, the kind of features you use. If you got the right features, if you use an SVM or a neural network or a decision tree, you get something different. But in a lot of fields, this doesn't make a huge difference. But if you don't have the right features, then it's a whole different business. Okay, so and the reason why this is an important point. The reason why we have not discussed this much is not because it's not important, but because it was and it still is to some extent an art. It's not something that is easy to condensate in few basic principles. It's an art, and it's an art that is problem specific. Okay, so what we try to do today is to somewhat push this a bit further and try to see what's common of some ideas that have been proposed in order not only to design but to learn phi. Okay, and in this perspective, when I say that learning works much better when you have the right features, quantitatively, you can view this as basically saying that you can get better result. What does it mean better result? That for a given budget of labels, you get a better performance. In other words, if you reduce the budget, if you have the right feature, you need fewer labels to achieve a certain accuracy. Okay? So the idea, if you want implicit in the statement that good features allow to do better learning, is that they allow to reduce the needs of labels. Okay? So to some extent, that point is a chicken and egg problem, because if you need labels to learn the representation in order to reduce the need of label, that's fine, but that's somewhat not the hope. And I think the hope of most people would be to somewhat be able to design good data representation techniques that are able somewhat to work in an unsupervised fashion and try to capture some of the important characteristic, features of our data in order to reduce the need of human annotation and to get labels. Okay, as we'll see, this story is somewhat bittersweet because we have ideas, but in the end of the day, labeled data seems to really give a big boost in performance. But today we're going to focus on unsupervised techniques. Okay, and in doing that, we're going to try to see how we're going to essentially review a bunch of different ideas and how try to see how they can all put under the same perspective. So we're going to consider unsupervised data. And again, using exactly the kind of notation that we used so far, we have a sample x1, xn, and we typically assume that it does come from a probability distribution that is now just a probability distribution. I guess I call it P. A probability distribution on your input space. Okay, there's no. We're not going to consider the output space, so this is only going to be the only distribution around. That notation there is a compact notation to say that the data are IID because they all come from P of X, and because they are independent, they just come from the product measure. So it's a useful compact notation to just say IID. And then what we want to come up with is some principle to learn phi, okay? And again, my promise to you is that I'm not going to do much statistics throughout my entire set of lectures. And again, this is going to be only the fact that they come from a distribution. You'll see where it enters, but it will only be a minor part of our story. So we want to learn phi. We want phi to be good for future tasks, okay? But we don't know what the tasks are, okay? We are given a bunch of images, and we don't know what kind of question we're going to ask about the images, and still we would like to get a good representation. So again, we have to come up with some principle that will allow us to learn good representations in an unsupervised manner. What do you think are some principles that you could use? In some sense, in other words, if you wish, we have the probability distribution. What was the other ingredient we used to define the supervised learning problem? A probability distribution and a loss function, right? So I gave you the first ingredient. In other words, what is the second ingredient, okay? How we define a loss function. And it's not clear, because what is the good measure of error? What is intrinsic in the notion of loss function is that you want to try to somewhat preserve something, okay? Make some error small. What is a good error measure here? What do you think? What do you mean? What do you mean by distorted, like distance-wise? Yeah, so one answer is if you want distortion, or I'm going to use the word similarity preservation just to be a bit more general. So one idea is that you have 2 points, x and x bar, and they're similar, okay? This is informal, okay? They're quite similar, okay? If you wish, their distance is quite small, okay? In the ambient space. And you would like to make a transform of the data. The potential is nonlinear, and that somewhat preserve this. So you would like to find the phi such that when you do phi x and phi x bar, they're similar. Not all of them are similar. Maybe all of them are similar, but typically what you want to preserve is some local distance, okay? All right? So this is not a loss function yet, and it turns out that in this class we're not going to discuss much this one point here, okay? We're just going to mention a couple of things quickly. And I guess the two things I can mention right away for you is, first of all, if you think of, you remember that we discussed sketching, the idea that you take the input matrix and you hit it with the random matrix S, or say, of Gaussian entries or things like this, and we somewhat show that in expectation the inner product were preserved, okay? And I somewhat said in passing that you can find a similar result for distances and with high probability. If you want that first example, again, it's not learning, okay? But the idea here is that you can define phi of x to be just S transpose x, and then basically you have that, you just have this kind of result, okay? More precisely, you have that distance in the phi is equivalent, this is equivalent to the distance in the original space. What this means is that there is a constant from above and below that controls this. So you don't lose anything, okay? In this sense, there is a distortion, but it's not big. It's exact in the sense that the distances are changed, but you can still discriminate every 2 points, okay? So that's one example. And this example already mentioned. There is no learning here, as I mentioned. You find a ton of approaches that go in this direction, where they basically try to, rather than learning a phi, they they learn a phi, but they start by basically saying that you want to learn a distance, okay? And the way you define the distance is just like this. Okay? So you just take, you just redefine the inner product by putting a weight matrix in the middle, okay? That's all. And this is, I guess the classical name is Malanobis distance, is one name you can associate to this. It's a pretty natural way to parameterize distances. It's kind of the linear way to parameterize distances, okay? And at this point, what you could do is that, given a bunch of points, xi, xj, try to come up with a way to essentially find labels, okay? And the labels could be, for example, go in the original space, take all the distance that are smaller than epsilon and call that 1, okay? Every 2 points. So say that yij is equal to 1 if xi minus xj is smaller than a certain threshold tau and 0 otherwise, okay? So you do a pre-processing where you say, this is exactly what I was saying here. You keep, when all the distances are small, you put that as a 1, okay? When all distances are, or maybe not as a 1, but what they are, okay? It's, we're sloppy because we're not trying to introduce an idea, not a precise recipe. The idea is you look at the distances. When they're small, you say similar. When they're big, they say dissimilar, and then you somewhat create labels, okay? Not label in the usual sense. It's like labels of pairwise comparison. Now you have a data sets where the inputs are pairs and the outputs are this kind of labels, okay? And then you try to come up with some loss function to estimate this W, okay? Yes?
But in this case, the identity matrix is...
Right. So the comment is, why don't you just take W equal identity, and you'll see that we'll keep it there. Of course, the answer is, of course, the problem is there, okay? In some sense, this is the first time that somebody complained, which is good. You can complain at multiple points of this story that if you just try to, for example, preserve similarity, identity would be extremely good, okay? So typically what we need to do is to, for example, here, what is the constraint is that we assume that the dimensionality of phi of x, okay, was smaller than d and n, okay? We need to somewhat compress. And of course, this is just one of the things we can do. So for example, we could ask the same thing here. We could say, make the rank of W small, okay? We could do that, okay? We're going to see that this is going to be, no matter what principle, in some sense, there's going to be a big difference. We're going to comment on it later. There is a big difference between supervised and unsupervised learning. Loss function is not enough to define a problem, okay? And if you want, this is the first time you see it. Yes?
The condition on y equal 1 or 0 based on distance less than tau. This distance is the new distance? Or
No.
original
It has to be, yes.
Original.
Yes, yeah. So the idea is that the original distance sucks, but not so much, okay? So when I cannot trust things that are far away, but things that are close, it's fine, okay? So imagine, again, a digit in an image where you just move it just a little bit, it's fine, but if you move it quite a bit, then it becomes not, the Euclidean distance of the pixel is not a sensible metric anymore, okay? It's, even that one is debatable, okay? But that's a starting point. If you look at what is called metric learning, so this is basically JL, Johnson-Lindström, and this is what you typically refer to as, is the starting point of most of metric learning, okay? Because this is a metric and we want to learn it, okay? And there are quite a few ideas in this direction. What we want to discuss is instead a different principle, okay? Yes? There is no loss. I didn't write it. I don't want to write it. Again, I just wanted to tell you that you could go in this direction, and we won't. We go in another direction. So the question, so the one question was the loss function here, and I just deflected it like this. And the second question was, what if the initial distance was not a good idea? It's a problem. You have to be, you pay him to sit down and say similar, not similar, and you are come out back to labeled learning, and then it kind of sucks. But you'll see that these kind of complaints about the need of constraints or the need of a good initial information, they're there, okay? In some sense, unsupervised learning is unsupervised-ish, because somewhere you need to have something you can, distances have to be meaningful in some way, okay? We're going to introduce now another principle, and you'll see that it's somewhat still there, okay? And it maybe is one of the issues why these things don't deliver as much as one would like, okay? Okay, so this is just a parenthesis, okay? We could do a full class on this, but we don't. What we do is that we introduce another principle, and perhaps you can tell me what is another idea. So this is idea one, okay? Given this data, try to preserve distances. Can you think of another idea? Not too far away, but yep.
Enhance differences, like to get, for example, more variance in MCA.
Right. So I guess one idea would be somewhat, maybe have some kind of repulsive thing instead of similarity, doing dissimilarity. But I would say that to some extent amount to changing the name of what you call similar and dissimilar, okay? And then you can do probably, I've been vague enough that we can put it in here, okay? But sure enough, depending on what you know about the data. But in some sense, the idea of this is that there is notion of similarity of some kind or dissimilarity of some kind, and that's your starting point, okay? I want to have something different. The keyword is reconstruction, and that's kind of probably even more popular than this, okay? And this actually requires a bit of work, because essentially the idea is I take the data, I represent them, and then I want to know how well I can reconstruct the data, okay? Which immediately, tells you that somewhat you need to go back. So whenever you do reconstruction, you have to introduce the reconstruction map, the going back, okay? So you have to introduce a map psi that goes from phi back to x, okay? And at that point, with this symbol, so this is called we're going to, map and error, I would say. Okay, this is the reconstruction map, and associated error, the idea is that now we can compose. This is just the composition, okay, of phi and psi, and now we can compare it. Oh, let me drop this. With the initial point, okay? So again, the data space, the representation space, I map the data, and then I go back and ask, how well am I doing, okay? So again, following the same kind of notation, the sloppy notation we used so far, that's the kind of idea. I would like to find a pair of representation and corresponding reconstruction such that when I apply them concatenated, I get a good approximation of the original point, okay? So few names, okay? So if we call this representation, the reconstruction is a pretty good name for this, okay? If you call this a feature map, sometimes this is called the pre-image of the feature map. And it's not really an object that is particularly well studied in the context of feature map and kernels. In fact, it's a kind of a nasty object. But let's look at the other names. So let's see, signal processing. What do you think is the name of psi in signal processing? Is an inverse transform, or any engineer in the room? Synthesis, okay? Analysis and synthesis. You have a signal, you decompose it, then given the decomposition, you go back, okay? So you can call it an inverse transform. Or a synthesis operator, I guess. In information theory, I guess you can call this a decoding, or an encoder and a decoder. And an embedding, I don't think there is a name. Okay, if there is, you let me know. But again, this is just to let you know how this, I think it's good to know that the same quantity, very related ideas appear in different fields. Because when you try to come up with ideas, it turns out that you're going to end up pretty close to one of this and change something, okay? So this is the reconstruction map. How do we quantify the reconstruction error? Here we write the loss function, also because it's particularly easy, and the loss function is simply going to be this, okay? The distance, okay? And what we want to do next is basically taking just a couple of steps, okay? One is just see how once you have data and once you have a loss function, you can at least start to do what we've been doing for a while, like empirical risk minimization, okay? Then you can stop a minute and keep on complaining, okay, about a bunch of different things, then fix them and try to go on.
Can we learn the inverse transform using some tools like neural networks or?
Yeah, you can neural networks, you can do everything, so yes.
That
No, yes, the whole point, so the question is, can you use neural networks to learn the inverse and so on? And, it's a map, right? So whenever you have a map, you can learn it. So we're going to get there. We're going to get on how the neural network picture fits here, but we're going to take a couple of steps into PCA, sparse coding, and k-means first, and showing how they also somewhat are ways to do that, okay? So sure, basically what I want to do right now is go from this to empirical risk minimization, okay? And basically say, okay, the principle here is over some set of phi's and psi's, minimize this. Because this part is nice and reassuring. You kind of do what we've been doing so far, right? It's kind of a problem where the output is a vector and is actually the input, okay? Okay, that's it. I didn't say, but it's natural to use the following name for the pair. The pair psi and phi with some obvious meaning is sometimes called an autoencoder. You want to autoencode. Yep.
You're always looking to map data into a lower dimensional space.
We'll see. So the question is, do we always look at maps that map data in lower dimensional space? Okay. We'll see that we actually be more general than that. As spoiled before, we had a spoiler before. In all these cases, you will need to make some assumption on phi and psi. So here I'm just repeating that, okay? And then we start to make assumption, and one of them will be lower dimension, then you can do others. So reconstruction map, reconstruction error, autoencoders, empirical risk minimization if you wish. But let's go back. If you want, we're going bottom up, but the idea when you do empirical risk minimization in supervised learning, as you do that, because you would like to find the best expected error, but you cannot, right? So the idea is that this is a proxy for the expectation over x of this. You would like to minimize the error on the data because what you really like to do would be to minimize the error on future data, okay? The reconstruction error on all possible points coming from not only the one in the training set, but also the one coming from the same distribution. And And here, we see even more mathematically how the comment of the identity being a trivial solution is true, okay? Again, as you pointed out a minute ago, if you take W as a distance to be an identity, you just do all the job, okay? Here, you have a similar effect. But you can see it from here that it's not only a thing about the training, it's about the test. Pick any psi that composed with is going to give you the identity, okay? For example, identity, okay? Not only is this a good solution for the data, but it's also a good solution for the test error. And so this shows that really this problem is not on the same ground with supervised learning. Supervised learning can go on by basically saying, I want to take a loss, I want to take a probability distribution, I define the target function, and I don't have access to it. I have the regression function, the median of the conditional expectation, median of the conditional probability distribution, I have the Bayes rule, and it's not like I can say, oh, it's going to be like that, okay? You don't have access to what it is. You need to approximate from the beginning. But here, this is not, so in some sense, in supervised learning, the hypothesis space and the assumption comes at a later point, okay? You say, here's the problem, and now let me try to solve it. And then I have to figure out what is a good assumption. Here, I don't have a problem until I put the constraint, because it's somewhat even more crucial. The prior and the constraints are even more crucial because each prior and constraint is going to define a different problem. So it's somewhat hard to compare different algorithms. Let me say in other words, if you pick, say, L1 or L2 for classification, L1 or L2 regularization for classification, they still solve the classification problem. Here with two different priors, but the problem is the same. Here we'll see that really every set of constraints defines a different problem, a reconstruction under a different constraint, okay? So there is something which is similar and something which is different. The part which is different is the fact that putting constraints here is extremely important. What we want to do now is describe one way to put constraints, which is useful enough to describe a bunch of different algorithms, okay? Any questions so far? So we want to try to learn phi. We want to try to do it in an unsupervised way because our hope that this will, diminish the amount of data that we need to annotate and get labels of. And then we need some, and we find out that somewhat related ideas are contained in a bunch of different fields, from signal processing to information theory. But then we want to focus on not only design but learning distributions. In one case, we did try to learn a metric, okay, or an embedding that preserves distances. Here we change point of view. We introduce a reconstruction map, which is somewhat a dual or an inverse of the representation, and we try to preserve the information in the data as defined by the distance of the size of the residual, okay, once we reconstruct back. Yes? No, it's going to be on the shape. So the question is, what is going to be the constraint about? It's going to be about psi and phi, the shape of psi and phi, okay?
Find the best encoding and best reconstruction given some particular distance. And the question will be, what is the best encoding and reconstruction?
Yes.
Given some specific metric.
Yeah. So the metric let me re-say. You define the problem. Let me re-say. So the question is, I want to find psi, that's my goal, given unlabeled data, okay? That's the problem, okay, in words. Then I try to formalize the problem as learning psi by also learning a phi that somewhat preserve distances, and I define this to be my loss function. I try to go on, and I discover that I have to make sense of this problem. I have to put constraints on phi and psi, okay? We accept the loss function. We don't try to change it, and we try to fix what's left. Of course, you can also go back and say, could I use a different loss function, okay? But we're not going to do that, okay? We just keep this because it's simple, and you can say, what if I put there a different kind of metric? For example, could you kernelize this, or can you put, an L1 metric, or you name it, okay? Yes, but in some sense, all those methods are somewhat similar. The real ingredient which is missing is the constraints on phi and psi. And so that's what we want to discuss. Other Comments? Questions? All right, so the idea is that among all possible autoencoders, we are going to consider, at least to start with, a family where psi is linear. Okay? So we're going to consider the case where x is equal to Rd, f is equal to Rp, and p can be bigger or smaller than d at this point, okay? Doesn't have to be. And then we consider phi linear, which means that phi is belonging to some set D, which is a subset of all matrices that are D by P. Yes, okay? That's the first assumption we make. This is linear. And the second assumption we make is that phi is what is sometimes called the nearest neighbor encoder, which essentially means that phi of x is going to be equal to the arg min over f of x minus psi beta square. So this is x. What is called the nearest neighbor encoder? Because basically you have x, you have the space of possible coefficients, okay? And this can be some subset, okay, of the full space. So f lambda here is some subspace of the full space of coefficients. So it's something like this. This is f. This is f lambda. Okay. And then you have the map psi that take all the coefficients, all the representation, and map it back to the original space. And then you want to, now x can be in this space or not. If it's not, you have to project. Okay. So this would be x. And this will be the corresponding psi beta, okay, that achieves this minimum, okay? So let's call this is also a beta star, right? It's a vector of coefficients, so this will be beta star or beta x. So this looks a bit weird, but you know, it's we're going to see that it's actually the way a lot of things work, okay? Lambda is just some set, so here f lambda is just some set, okay? You know, for example, this could be an L1 or an L2 ball in the space of all possible coefficients. So I take Rp, but rather than working with Rp, I take a ball in Rp, okay? A constraint, or it can be the whole set. Sorry, this is a beta. Okay, so give me x. Or if you want, let's start from here. You are in the coefficient space. You can apply now the reconstruction. And for each coefficient, you're going to go back in a point in the original space. Okay? And then among all the possible coefficients, you select the one that gives you the best distance to the input you want to try to reconstruct. Okay? We're gonna explain this, and you're gonna see much more clear. You know, it's gonna be much clearer than this. Here, just notice that this is the nearest neighbor name, where the nearest neighbor name come from. Okay, so leave it there 1 second, and then we look at this and see what it means. So let's comment on those two assumptions, okay? First of all, once you make that assumption, it's very tempting, and what is typically done is called psi a dictionary. Okay? Because now you can view psi as also as the collection of it's columns, okay? And these are called atoms. Why? Because if you now do psi beta, you can just write this as the combination of the ij from j from 1 to p with coefficient beta j. Okay, so beta j here is just one entry of the vector beta. So if you assume that decoding to be linear, the action of a decoding is taking a bunch of coefficients and combine them linearly to get back the input points. Okay? So a linear decoding you can view as a dictionary of things, atoms, a generalization of a basis. And when you try to reconstruct, what you do is that given a set of coefficients, you try to combine them, to combine the atoms linearly with these coefficients. Okay? So when you do x minus phi beta, it means that you try to find the set of coefficients is like when you decompose a signal on a basis, okay? Only here, as you see in a minute, you don't know the basis. You also try to learn it, okay? So here, in this kind of formulation, you don't know psi and you don't know phi. If you knew psi, if you knew the dictionary, finding beta would be just finding the best possible coefficient on that thing that you can think of a basis, but needs not be orthonormal or linearly independent. Okay?
So find the best linear combination that gives you x.
Absolutely. Okay? So what you just said is find the best linear combination that gives you x. And if you want this, find the best linear combination that gives you x, and also find what you have to combine. Because here the problem is you don't know a beta, but you also don't know the EIs, because the EIs compose psi, and psi you don't know. Okay? So now, again, let me rewrite the psi, the phi. And I just rewrite it, with that notation. Okay. Now you see it more clearly. If you add the atoms, you just have to do the decomposition of x on those things. Okay? Let me do one more step, and then we comment a bit on what we did. So in the empirical risk minimization framework, we wrote the problem as this. But if now I define psi and phi, I assume that they have this form, I can now rewrite the problem. Phi xi is simply some coefficient at the, well, let me just drop this and hopefully it's clear anyway. Oh no, let's write it. So I. Okay? So phi xi is defined to be exactly the beta that minimizes this. Okay? You have two different ways of writing it now. So I can now rewrite phi this way. So again, if I had the dictionary, I would just have to expand my function. But I don't have the dictionary. So you also now have to find the dictionary itself. Okay? So if you assume your autoencoder to have this form, the one where the decoder is linear and the encoder doesn't have to be linear and is defined by a nearest neighbor encoding, that is somewhat find the best metric projection on some set, then you can write the problem this way. And you can view this as learning the dictionary. Okay? And this is what is typically called, oh, maybe we can just give the whole name to the whole thing. This is what is called dictionary learning. Okay, so it's a form of learning autoencoders where we assume the decoder to be linear and the encoder to be potentially nonlinear, but having this form, which is pretty general. Okay?
So, how does PCA fit here? Does it
That's what we do now. So what we do now is that showing how this, what I wrote there, now the game is going to be, we want to choose D, calligraphic D, and F lambda, and we're going to make 3 different choices, and we're going to get PCA, sparse coding, and k-means back. And we're going to see what is the corresponding dictionary and encoding and how they compare to each other. Okay, that's exactly what we want to do now. And at this point, this part is actually, so this is a bit abstract, but it's just because I introduced a common formalization of all these problems. But at this point, we just have to make choices and turn a crank and look at them and realize we find stuff that presumably you have seen before, if you didn't lie when you said that you took a machine learning course before. So, example 1, PCA. And I guess PCA where I'm sloppy about the recentering, okay? I don't care about recentering. I just do the covariance, the second moment matrix, and I. So the idea here is that D is the set of matrices. So F lambda is equal to RK. And here K is going to be the, well, I guess we call it M before. Let me call it M. Is the size of the PCA, how many components you want to keep. So typically this is going to be smaller than N and D. Okay? So here, this is just a matrix which is D by M. And now we make the assumption that this matrix is providing you a set of k vector which are orthonormal, okay? So the columns of, so we're basically saying we want to find a dictionary which is an orthonormal basis of Rk, okay? Or rather of a k-dimensional subspace of Rd, okay? So not only we want to find a dictionary, now we can really call it a basis in a very precise sense. A set of orthonormal vectors. How many? K of them. So it's not a basis from Rd, but it's a basis from a subspace of Rd. Okay? So here's the choice for F lambda. So there is no lambda here. If you want lambda is equal to M, is that's the parameter. Maybe we can call it just Fm. Okay? And then this is the main restriction we have. Okay? So now we have to just take this and plug it in here and see what happens. Okay? Before we do that, let's just remember what is this. This is the projection. Okay, this is the map that goes from Rd to Rd and projects on the span of the A1, AK. That makes sense? So, again, you have A1, AK, in this case I adjust A1 and A2, and they are vectors in Rd, and they span a subspace of dimension k, okay? The inner product with these vectors is going to be an identity matrix, a k by k identity matrix, but the d by d matrix is actually a matrix of which projects points in there. Okay? Is that all right? That's again just basic linear algebra. Now, let's look at what phi is doing. Phi is doing what's written here. Here, or there, I guess it's even better. But you have now that psi star is the psi is orthonormal, meaning that you have a psi star, they're joint, and when you compose them, they have nice properties that we just reminded here. So if you take it's really easy to see. You just take the derivative, set it equal to 0, okay? And what you find out is that the best possible beta is simply given by psi star applied to x, okay? That's really easy to see. Do you see it? If you do the derivative, you get twice psi star x minus psi beta equals 0. The psi star hit x, the 2 doesn't matter. Psi star hit x, psi star hit psi here, and gets you the identity. And so you go back there, okay? So it's just an orthonormal basis. It's really what you happen when you try to find what is the best possible, given orthonormal basis, given a vector, try to find its best decomposition on that orthonormal basis, that's all. Which means that we now can go back and rewrite the problem just as a function of psi. Now we can stop 1 second, look at the equation, and ask ourselves, what does it mean? It just means that we want to find the projection, the best k-dimensional projection of the data on a linear space. Okay, or in other words, we want to try to find what you might call the subspace learning problem. Okay, here in this case is this is the subspace learning problem. You can view PCA as a basic subspace learning. Okay. Among all the possible, in this case, 2-dimensional subspace, I want to find the one that fits the data best. Okay? So this is just another view on PCA. It's just the same. Okay? If you go there and just in one line, you can find out that all the usual stuff that you know about PCA. It's just that now you view PCA as a way to learn a dictionary. Okay? So if you do dictionary learning, assuming the vectors to be orthonormal, you get PCA out, and you find out something which is somewhat obvious, that when you make a constraint, you can view it as a geometric constraint, or where the data should lie, or the shape of the probability distribution of your data. For example, in this case, we're assuming that the unsupervised data should lie close to a linear space, okay, something like this, and we just try to find it. Is that okay? So it's just plug and play, okay? So what we did is just we took the general formulation of linear decoding and nearest neighbor encoders, which choose psi to be a linear map of matrices that are orthonormal in this sense. We plugged them in, we just took a derivative, and that's what we get. Okay?
Phi star is a projection of
Yes.
on the plane or whatever the space spanned by the columns of
Psi. Yes. And you have to find them all. You have to find the columns, or in other words, you have to find the psi, or in other words, you have to find the projection. Okay? Okay, so we don't do it, okay, but you can go here and put, let me call it a lower psi here and here, and then you get kernel PCA. And from kernel PCA point of view, you can basically assume, what if my data, lie close to a curved space? But we already did this calculation. It's just that we just have a new interpretation for it. But now you see how it fits somewhat the unsupervised point of view. And at that point, it's a bit more complicated. You're trying to do some kind of nonlinear subspace learning. Okay? So we skipped that at once. Example 2 is probably the most famous. It's called sparse coding. So in this case, F is our P, and typically P is bigger than D. Then F lambda is actually typical the beta in F such that the norm 1 of beta is smaller than 1 over lambda, and psi is just linear, no constraints. Okay? This is particularly easy because all you have to do is that you have to, or maybe let me just write it in this formulation to make it even clearer. So you don't make any you take the dictionary size to be much larger or larger than the data dimensionality. Okay, so here you want to try to find a dictionary where the data can be written as a sparse linear combination. That's the idea. Okay, so you for each x, you would like to find an expansion with most of the betas are 0. That's the idea, okay? It's an encoding, but it's an encoding which is sparse. As you see from the equation that I just that I hide here. When you perform this, there is no reason to get the sparse set of coefficients, right? Typically will not be, okay? In sparse coding, you want a sparse representation. You want the beta to have a lot of zeros inside. So what do? One, you allow yourself to use a huge dictionary. The hope is that if I let P be large, then I'll be able to find some atoms that describe really well my data, okay? And throw away something else. Sorry. And then what you do is that you ask for sparse representations. Okay. So we've seen last class that what you do. This is just the same as we did the trick when we wanted to try AJ were the inputs, the component of xi were the outputs, and we just wanted to find a sparse solution. Okay. Here for each x we cannot try to find the same. Okay, it's a completely different interpretation, but mathematically it's exactly the same thing. We had the vector of y's and want to find the best sparse representation on the x's. Here we have an x, and we want to find the best possible sparse representation on the A1 AP. Okay, that makes sense? In that case, we had n points, so the vector of y was n-dimensional, and we had d dimension. Here we have d-dimensional vectors, and we want to use p elements of the dictionary, okay? But we don't know. The big difference is that in that case, y and x were given. Here, the A1, AP are not given, so I have to find them, okay?
So if you make B large, what's the point of making that a sparse? I mean, it could be sparse, but relative to D, there could be there could be more than D non-zero.
Absolutely, absolutely. So what he's saying is, here I might get to a point where the representation is so I have a vector set which is 5 times D. P is 5 times D, And the sparsity level is bigger than D. Then that, well, that's not possible. I think you get D at most, but that's a fair question. Okay. Here the idea is that that's up to you. Okay. In some sense, that would be a sign that this is not a good idea. That this is not, or that you have to force, this lambda to be even. What is it? Bigger, so that this becomes smaller and you compress more. Okay. Here, in some sense, you have you control this, okay? And so if you want m above and lambda here, play the role of the compression coefficient, okay? And somebody asked me, do you always have to take the dimension of f to be smaller? Well, this is an example where you don't, right? You actually allow yourself to work in a much bigger space, but then you try to somewhat compress it back. Okay, you still eventually take a representation which is shorter in some specific sense than the one above, in the one you started with, but you allow yourself to at least search in a larger space. Okay? So here we can make another couple of comments. One is, how do you compute this thing? Okay, how hard is it to compute this thing? Yes?
Just to understand, either you start from a smaller and you expand and then you recompress, or you start large and compress.
Say this is RD. Okay? Well, let's do it again. So this is RD. You start from a page which is much larger. So this is RD, the space of signals. This is RP. This is called the redundant dictionary. Okay? A1, AP are a redundant dictionary. They can express more. But then what you try to find is the set of coefficients here that best represent this. Okay? And these are not just a subspace, and we're going to explain in a minute. They're more complicated than just a subspace. So input signals are a certain size. The potential set of vectors that you can span is much larger, but then you try to find within this larger set a set of coefficients that will explain back the original data. Does that, okay? And perhaps this motivate the following question, which is, okay, in the case of PCA, we were assuming the data to lie close to a m-dimensional subspace. What is the geometric assumption underlying this model? So, if you don't know the answer already, it takes a minute to think about it, to realize what it is. Perhaps the good hint is think about the fact that assume for a minute there is just one dictionary that on which all the points have exactly the first half of the components different from 0, and then everything else is 0. Make sense? So you take each x, you found the magic dictionary for which the first half of the components of every x is different from 0, and the second half is different from 0. Okay, so this is the space of x. What is the shape of these points when I represent them? Is that clear? You have vector of size d, but you show that you only need d half atoms to express them all. So this would be a subspace. It's a subspace. You have a linear combination of d half spanning everything, right? So it would be a half space. Okay? Okay, but maybe this is this would be nice, okay? But then I can use PCA. Suppose now that what you find out is that the first half of the data can be described by the first half of a dictionary, but for the second half of the data, I need the second half of a dictionary. So now you can play the same game with the first half and the second half, okay? You have the first half of the dictionary is going to span this subspace and is going to be good for the first half of the data. The second half of the dictionary is going to span, now this gets very complicated. Why did you laugh? It's perfect, right? So this is one subspace, and this is the other subspace. And you can if this is me, don't make me draw 3 because then it would be sad. So, but this is, it's almost fine. It's okay. Anyway, so that's the assumption you make when you say sparse coding. You assume that your data lie in what is sometimes called a union of subspaces. Okay? Because it's a union of subspaces. And of course, clearly this is much, and why do I have to go freak out? Because we didn't put an offset. So they always have to go somewhat through the origin in the same way. Okay? If I allow myself to put an offset everywhere, and this is not too much of a sweat, then I can put, a bunch of subspaces floating around happily. 54? No, this is the setting where P is much larger than D. No, we just did two cases, right? So we did one case where D is 100, and then, D is whatever it is, and then we just did two cases. Like the PCA is here. So we took this to be M smaller than N and D because it's PCA, whereas here is still the story where I try to just make P. It's okay. I'm happy it was not me, just. You made P as large as possible to then try to be able to find this sparse linear combination. So P is as large as you can handle, and then you just try to find here the best subset. So I guess maybe the confused thing is what is the size of this? This is implicitly controlled by lambda, right? We saw in the sparsity class that this is just a constraint formulation, right? Here I'm just trying to make, and I guess this is confusing, so maybe let's just call it R. Okay, the same, so my brain doesn't get confused. You're just trying to say when R, you can pick R. When R is very small, what do you expect? That you're going to get very sparse representation, okay?
In your example that you said half of the coefficients are explained
right.
separately. In that example, P is
No. In that example, so the question is, in the example where I did half of them, how big is P? I don't know. P typically is going to be much larger than D. So if this is this is a three-dimensional space, or at least I'm trying, and that P could be, I don't know, 100. Okay. So this is a magic number. You can call it S. Okay, which depends on the way you choose R. Is the sparsity that you want for vectors, and this is implicitly controlled by R. In my example, yes. And that half is, there is not something where you say half. You have to implicitly say R, larger, smaller.
But the claim is that if you take the L1 wall, it enforces some kind of L0.
Yeah,
sparsity.
yeah. This is the claim just recycled from last class.
But it's more complicated. Is that because you want to learn the
Yes,
dictionary?
absolutely. So the comment is, again, I'm recycling last class. I'm giving last class for granted. We know that given a dictionary, L1 is going to be a proxy from L0, and so if I make L1 small, I get sparse solution. And then the difference is simply that here I use it in a different way, and also I try to learn the A1, AP, okay? So in that case, xi were given here, it's a different game. Okay, but again, the main novelty here is that the data don't lie on one subspace, but a union of subspaces. We cut the story short from a computational point of view, because essentially the main observation here is if you had A1, AP, the problem would be convex in each of the beta I. So this problem separates nicely on the beta 1, beta n, okay? And each problem is essentially you can solve with techniques like the one we described last time, the proximal methods, okay? Some kind of iterative software shoulding of some sort. If beta were fixed, so you don't have to do this, that's convex in the A1 AP. You have to solve it for a matrix, okay? You have to find the matrix, but that's a convex problem in the A1 AP. Annoyingly, the problem is not jointly convex in both psi and betas, okay? So considerable amount of work has gone in the last 5-10 years to try to prove that there are conditions that under which this can be solved. Most approaches go on and just try to do, whenever you have a separately convex, non-jointly convex problem, you typically cross your finger and you do alternating minimization, okay? So you optimize, you initialize, optimize, or fix a dictionary, optimize over beta, then update the dictionary, and then you keep on going a few times. And you can do gradient descent all the way to the end or part of it. That's not the whole point of this. The main point is each of the two separate problems is relatively easy, and you already know the techniques to solve them. In both cases, you can use essentially projected gradient or proximal gradient. The big difference is that the problem is not jointly convex, and so in general, you will not have any insurance to converge to a global minimum, but only to a critical point. Okay, and that's always the case. In some sense, the PCA is the only place where there is a miracle. Even in that case the problem is non-convex, there is some structure hidden in that specific problem that allows to just solve an eigenvalue problem. For this, that's gone. Okay, so in general you have to make some assumption on the data distribution and so on. Yes. Yeah, sorry. Yeah, sorry, I forgot here. So these are, you typically, yeah, so here this is not all linear. What you do is that you take the psi such that the AJ have norm 1. So exactly what you're saying, I forgot about this. So you want the column of the dictionary to be normalized because otherwise you have some rescaling that can go on. I forgot about this. And that's why I always say you have to do some projected gradient when you optimize over the psi. So this is now psi belonging to this calligraphic D. Okay? Absolutely, thanks. So,
When delta is fixed, basically we retrieve the old problem of the last lecture.
No, the other way around. When psi is fixed, you retrieve the problem of last lecture.
Okay.
Right. So what the observation is when psi is fixed, you just recover the problem of last lecture, where instead of trying to predict the y's, you try to predict the x.
Yeah.
Okay. But here we also want to, we don't have the inputs, we just want to find it somehow. Okay, the last example I want to make a bit quickly because I want to say a couple of things are, take fk to be, so the third example is k-means. K-means we typically think of as a clustering algorithm, but it also can be considered as what is called the vector quantization algorithm. Here we take that point of view. And so E1, Ek is an orthonormal basis of Rk. Okay, so for example, E1 is simply 1, 0, 0, 0, 0, 0, okay, and so on and so forth. So it's not a continuous set. It's a discrete set of k element, okay? And this is the case where this one can be anything, you know, okay? It's just a linear thing. We just write it down again. That's it. That's just k-means, okay? It's not k-means probably in the usual way you see it, sorry, because here we take more of a dictionary learning perspective on it, okay? Again, fk is not a finite dimensional set, it's a finite set made of k vectors, okay? So we want to just convince ourselves that this is the usual k-means, okay? And perhaps the easiest way is to, is to think in terms of the corresponding computations. Again, this problem will not be convex jointly in each one of them, but is separately convex. And so again, you can do alternating minimization. Now, if you pick psi, okay, when you do psi ei, you're just selecting the ej, you're just selecting the kth column of ej, okay? That's all you're doing. So when you do this problem, let me rewrite it. You just try to find the E1 among no. You want to try to find, no, yes. among E1, EK, let's do for every point. What is the meaning of this? This is the first step. I give you the dictionary. Now I try to solve the representation problem. What does it mean? If you can view it as an assignment, you can view it in two ways. You can view it as an assignment or a super duper sparse representation. It's a super duper sparse representation because the coefficient that you allow yourself to use for each point is super sparse since it only has one component different from 0, and it's exactly 1, and all the other coefficients are zeros. You don't allow yourself to do a linear combination of the atoms. You allow yourself to use one atom. And in that sense, that's an assignment. Okay? Each point is going to be completely represented, encoded, by one atom, one of k. Again, clearly here, k is the k of k-means, in the first part. And typically, k here you would want to put certainly smaller than n, otherwise each point can represent itself, and that's done. Is that okay? So that's the first step. So in this sense, you can view k-means. This is the vector quantization point of view. Given a set of means, what you do is that you just find a very sparse combination of each point, which in the end is just going to be representing each point with one element. So you represent each point with the sparse vector, and you reconstruct each point by the nearest centroid, which is now just a column of this matrix. Okay? Again, this is a standard point of view of k-means. That's when you look at vector quantization point of view, this is exactly what you find. But here, just you find it somewhat easily as just another example that take PCA and sparse coding as other choices. I would like to skip the second step, which is the one that shows that if you now have for each B1 the corresponding encoding, this is an assignment that tells you, okay, let's say I take k equal to 2, the first half of the point is assigned to this mean, the second half of the point is assigned to this mean. Now you have to somewhat do the update of the dictionary. And this becomes to recomputing the means. Okay? That's the usual second step of Lloyd algorithm to solve k-means. So the first step is assign each point to the means you initialize with. The second step is just recompute the means. It's just that now you can view the means as atoms of a dictionary that you're just updating in this technique. Okay? So means and atoms somewhat become the same thing in this perspective. And k-means can be seen as an extreme version of sparse coding that only try to keep one component different from 0. Okay? Make me make just one small comment. In all these problems, we try to find a matrix psi, and then a set of B1, Bn of coefficients that we can think of another matrix B. And for the way we put the problem, the minimization over the beta is done separately over each B1, Bp. The minimization enters the sum. But more generally, you could think of other models that somewhat are not a dictionary learning model, where you minimize over phi and beta okay, so where you somewhat put different constraints at nearest neighbor. You drop the nearest neighbor encoding assumption, and you really just try to do a minimization over psi and b. And you can rewrite these simply as the db square in Frobenius norm. And you can just view this as some form of matrix vectorization. Okay? So you have a matrix X, and you want to decompose it in a D and a B. And we just chose a very specific form of B that allows ourselves to decompose the problem in this nearest neighbor technique. Okay? So one direction in which you can expand this is just go and look at other way to do matrix vectorization that will not constrain yourself to these kind of techniques. Yes?
What is Frobenius norm again? Like the maximum or the...
Is the trace of the square of the singular values. Okay? Is or this. Okay? is the trace of the sum of the square of each singular values, or that thing there. Okay, is the L2 norm of matrices. Okay, this is observation 1, and observation 2 is that you can actually go on, and let me just tell you what the last 30 seconds. You can also assume the following shape of, if you want to go beyond linear, you could assume, in the spirit of this, something which is a nonlinear version of this. And one choice we're going to start next class with is this one here. You do something that reminds you of those nonlinear sketching we discussed when we discussed random features, but now these are weights you want to learn, okay? And this is your representation in some kind of a linear plus nonlinear representation. This is a component-wise nonlinearity. And then you do the reconstruction this way. And notice that here and here you use the one matrix and then it's transposed. So it's somewhat you couple the encoding and the decoding, but they're not linear anymore. Of course, this becomes more complicated because now everything is not only non-convex but non-linear, okay? And what we'll see sometime, and this is one way to go from this kind of, at least in this game, at one between the encoding or the decoder was linear. This would be a case where we go away from that. You allow both the encoding and the decoding to be non-linear, and it's easy to see that this one can be seen as a form of basic neural networks. Okay, so this is, if you want to solve this, you can view this as a neural network that encodes itself. So next class, what we're going to do is we're going to do neural networks, and we'll continue the discussion and viewing neural network as a way to learn representation, either in an unsupervised way or in a supervised way. All right, sorry for the overtime.